The next part discusses equilibrium constants for reactions involving gases. Notice in the prior equilibrium we were always dealing with aqueous solutions in terms of concentration units, molarity. So we were really calculating what we commonly call Kc, concentration in molarity. I often see these expressed as kPs where we're dealing with pressure, typically in atmospheres, or sometimes we'll use millimeters mercury. A third unit we're familiar with from our gas laws is the kilopascal, kPas. So pressure is a way to measure the concentrations truly of gaseous reactants and products. The more reactants and products in the gaseous phase, the more pressure that they would exert. So therefore, we can use an equilibrium constant expressing ratios of partial pressures of each of the gases. Notice the adjectives, all gases all the way through, and every one of them must be a gas in order to share a Kp equilibrium expression. Still the same idea. If before we talked about concentration, notice how we used brackets to notice molarity. In Kp's, we use partial pressures. The partial pressure of product C raised to the power of the coefficient times the partial pressure of product D raised to the power of its coefficient, set over the partial pressure of reactant A raised to its coefficient times the partial pressure of reactant B raised to its coefficient. Brackets are molarity units. These capital P stand for pressure. The partial pressure of each ingredient. Products over reactants, coefficients become powers with which they're raised. Kc, concentration in molarity. Kp, partial pressures, typically in atmospheres. If we're calculating Kp, the partial pressures are always atmospheres, ATM. Standard pressure is 1 atmosphere, 760 torr, which is millimeter mercury, and 101.3 kilopascals on the metric standard international system. 1 atmosphere is standard pressure. The values of Kp and Kc are not necessarily the same because a reaction could have a mixture of solution with gases. We could have aqueous reagents, we could have gases with pressure. So there would be a difference in the units. Kp and Kc are only equal when the same number of moles of reactants and products in the gaseous phase are indeed 0. Delta N, where N stands for the difference in the number of gaseous moles of products compared to reactants. Kp, the equilibrium constant expression expressed in terms of partial pressures, can be found from knowing the Kc, the equilibrium constant from the molarity concentrations, times RT, R is our gas constant, and if we're using atmospheres, this is our old Puvnert days, 0821, and T is the Kelvin temperature. Delta N is the difference between the number of gaseous moles of reactants and products. Kp is found by taking Kc times RT raised to the delta N. R is our gas constant we introduced back in our gas laws, Puvnert. T stands for the Kelvin temperature so that we have no negatives or 0. And delta N is the change in the number of moles from products and reactants. We're comparing the number of gaseous moles. So let's peek between this and an example. Deriving that very relationship, let's suppose we have a molarity of a concentration with respect to A. Molarity is defined as moles per liter. So N represents the number of moles, and V represents volume in a liter. That's literally the definition of big M. Molarity is moles per liter. So the concentration unit is what this bracket represents, is molarity, expressed with moles of solute A in liter. V represents volume of a gas. A represents a concentration unit, and clearly I can see the number of moles being pulled out from that. We know that PV equals NERT from our gas laws. PV with respect to A, set equal to nRT with respect to A. And if we simply substitute in pressure of A, nRT, come up with our equation where we had said Kp can be found by knowing Kc RT raised to the delta N. If PV equals NERT and inside a PV-NERT problem truly is a molarity unit, moles per liter, we're just rearranging PV-NERT to say pressure is equal to mRT, P equals MERT. Pressure is equal to molarity times our gas constant R times our Kelvin temperature. This slide really is just indeed proving to you that there's a relationship between the number of moles per liter and the pressure unit, all derived from our ideal gas law, PV-NERT. So the relationships between Kp and Kc can be found by simply taking products over reactants, where either we use concentration units or partial pressure units, and showing us over and over that the difference between products and reactants, rearranging gaseous moles, comes up with our equation to convert between them. We don't have to rearrange every time, we just have to see it once and say, okay, I believe them. Kp can be found by knowing Kc times RT raised to the delta N. R is the gas constant, T is the Kelvin temperature. All of this is just algebraic proof of how we derive one unit into the other. Let's use it more importantly. Let's figure out if I know Kp, we can find Kc, or vice versa. Equilibrium constants for pressure and for molarity. Here we have an equation, and I'm just going to rewrite it down here. 2 units of NO plus an oxygen is in equilibrium with 2 units of NO2. We're given the Kp as 2.2 times 10 to the 12th power at 25 degrees Celsius. So we know Kp for an equation. We'd like to know Kc. So find Kc given a Kp. Algebraically, Kp is equal to Kc times RT raised to the delta N, kind of the formula that we're practicing here. Alrighty. We know Kp. We'd like to